But the other thing that people often build into these kinds of systems is something called attention, which is actually a pretty good metaphor, where in the same way that you would have networks that decide which parts of your hidden state to hang on to or which parts to forget, or those kinds of decisions like gating and stuff, you have a system which is deciding which parts of the input to pay attention to, which parts to use in the calculation and which parts to ignore. And this turns out to be actually very powerful. So there was this paper, when was this? 2017? Yeah. So this is funny because this came out the same year as the video you have about generating YouTube comments. This is in December. I think that video was October. Ancient history now, right? We're talking 2 years ago. The idea of this is, as it's called, attention is all you need. They developed this system whereby it's actually it's a lot simpler as a network. You can see on the diagram here, if you compare this to the diagram for an LSTM or any of those kind of variants, it's relatively simple. And it's just kind of using attention to do everything. So when you made that video, the LSTM type stuff was like state of the art. And that was until a couple of months later, I guess, when this paper came out. The idea of this is that attention is all you need. That like this stuff about having gates for forgetting things and all of that kind of stuff. In fact, the whole recurrence like architecture, you can do away with it and just use attention. Attention is powerful enough to do everything that you need. At its base, attention is about actively deciding in the same way that the LSTM is actively deciding what to forget and so on. This is deciding which parts of some other part of the data it's going to take into account, which parts it's going to look at. So you can have attention from the output to the input, which is what that would be. You can also have attention from the output to other parts of the output. So for example, when I'm generating in that sentence, like Sean came to record a video, whatever, by the time I get to generating the word him, I don't need to be thinking about the entire sentence. I can just focus my attention on where I remember the name was. So the attention goes to Sean, and then I can make the decision to use the word him based on that. So, so rather than having to hang on to a huge amount of memory, you can just selectively look at the things that are actually relevant, and the system learns where to look, where to pay attention to. And that's really cool. Like you can do it, there's attention-based systems for all kinds of things, like not just text. You can do, like suppose you have your input is like an image and you want to caption it. You can actually look at when it was outputting the sequence and you can say, when you generated the word dog, what was you can get like an attention heat map and it will highlight the dog because that's the part of the image that it was paying attention to when it generated that output. It makes your system more interpretable because you can see what it was thinking. And sometimes you can catch problems that way as well, which is kind of fun. Like it generates the output that's like, a man is lifting a dumbbell or something like that. And you look at it and it's not actually correct. It's like, it's Arnold Schwarzenegger, he's drinking some tea out of a mug, right? And what you find is then when you look at your outputs where it says dumbbell, you look at the attention and the attention is like mostly looking at the arms. That's usually somebody muscular who's lifting the dumbbell in your photos. And so it's overriding the fact that this kind of looks like a mug because it was looking at the arms. So the idea is this system, which is called a transformer, is a type of neural network which just relies very heavily on attention to produce like state-of-the-art performance. And if you train them on a large corpus of natural language, they can learn to do very well, right? They can be very powerful language models. We had the example of a language model on your phone that's like very, very basic, and then trying to do this with neural networks and the problems with remembering. And so you have like recurrent systems that keep track of, they allow you to pass memory along so that you can remember the beginning of the sentence at least by the end of it. And things like LSTMs, there's all these different varieties that people try different things that are better at hanging on to memory so that they can do better at, they can have longer term dependencies, which allows you to have more coherent outputs and just generally better performance. And then the transformer is a variant on that, well, is a different way of doing things where you really focus on attention. And so these are actually not recurrent, which is an important distinction to make. We don't have this thing of like taking the output and feeding that back as the input and so on every time. Because we have attention, we don't need to keep a big memory that we run through every time. When the system wants to know something, it can use its attention to look back to that part. It's not like memorizing the text as it goes, it's paying attention to different bits of the text as it thinks that they're relevant to the bit that it's looking at now. And the thing about that is, when you have this recurrent thing, it's kind of inherently serial. Most of the calculations for this, you can't do them until you have the inputs, and the inputs are the output of the previous network. And so you can't do the thing that people like to do now, which is run it on a million computers, and get lightning fast performance because you have to go through them in order, right? It's like inherently serial. Whereas transformers are much more parallelizable, which means you get better computational performance out of them as well, which is another selling point. So they work better and they run faster. So they're really a step up.